The year of 1905 is called Einstein's miracle year. In 1905, as a Swiss patent clerk working on physics in his spare time, Albert Einstein published 4 landmark papers on photoelectric effect, Brownian motion, special relativity, and mass energy equivalence. In the next few lessons, we will be studying his photoelectric effect. As we discussed in the 4th modern physics lesson, in 1905, Einstein proposed that light comes in as discrete packets called photons, each with energy hf. With that assumption, he could explain the mysterious photoelectric effect that was first observed by Heinrich Hertz in 1887. Einstein was more or less a paper-pencil kind of physicist, so he did not carry out the experiment. It was in 1913 to 1914 that Robert Millikan carefully performed the experiments to show that the experimental results fully agreed with Einstein's photon theory. Now let's take a look at the photoelectric effect experiment. This is an evacuated glass tube called a photocell. These 2 electrodes are connected to a power supply with adjustable voltage and an ammeter. One of the electrodes is our sample metal plate. When the photocell is in the dark, the ammeter would read 0. Of course, that's because the electrodes are not in electric contact. However, if we shine a light with high enough frequency at the sample, there would be a current in the circuit. The idea is that when the electrons in the sample get enough energy from the light, they can use that energy to overcome the thing called work function, which is like ionization energy, and the electrons can leave the atoms in the sample. Once these electrons leave the sample, the voltage from the power supply would push them to the other electrode and produce current in the loop. A battery tends to push positive current out of the positive terminal and the negative charges out of the negative terminal. With the power supply's polarity like this, it has a tendency to push the negatively charged electrons that way. That's why the freed electrons can move to the other side to produce current. According to the photon theory, an electron can capture 1 photon at a time. So it gets that photon's energy hf. If that hf is enough to overcome the work function phi, the electron gets ejected from the sample, and the ejected electron may have some energy left, the hf minus phi. And that leftover energy would be the maximum kinetic energy of the electron. This is the maximum kinetic energy because for inner shell electrons, it takes more than the work function for those electrons to be freed. So those electrons would be ejected with less kinetic energy than this. Because each electron has to get enough energy from a photon to overcome the work function to produce a current, there is a minimum frequency required to produce a current. This minimum frequency is called cutoff frequency. And the work function phi equals to the hf of the cutoff frequency, because at the cutoff frequency, the photon barely has enough energy to overcome the work function. This cutoff frequency's corresponding wavelength is c over lambda, the threshold wavelength. We can also measure the maximum kinetic energy if we flip the polarity of the power supply to this way. A battery tends to push positive current out of the positive terminal and the negative charges out of the negative terminal. So now, this voltage would be trying to push negatively charged electrons back this way. We can slowly increase this backwards voltage until the current stops completely. This voltage would be what we call stopping voltage or stopping potential. An analogy for the stopping voltage would be this. If I throw an object upward, I give the object some kinetic energy, and this object would go up to a maximum height, losing its kinetic energy along the way. This is like the electron with that maximum kinetic energy. Adjusting the backwards voltage is like adjusting the ceiling height. when the ceiling just exceeds the maximum height, the electron won't be able to reach the other side to produce a current. That's when all the kinetic energy of the electron turns into potential energy. So the maximum kinetic energy equals to the potential energy U, and U equals to QV. We're talking about electrons, so the Q is E, the elementary charge, and the V is the stopping voltage, when we use V0 for stopping voltage. So the maximum kinetic energy equals to E times V0, and it equals to the leftover energy the electron gets. The HF, the photon energy, minus the amount used to overcome the work function. So these are the equations we use for photoelectric effect. Please note that the work function is a property of the sample. A different metal sample would have a different work function. For example, the work function is 2.46 eVs for sodium and 4.08 eVs for aluminum. Because work function decides the cutoff frequency, and therefore the threshold wavelength, both of these also depend on the sample used. And this HF's frequency is the frequency of the actual incident light, which may or may not be the same as the cutoff frequency. Now let's look at a couple of graphs. For the maximum kinetic energy versus frequency graph, we can use this part of the equation. This is our y and f is our x. That means we should get a straight line with a slope that is h. And because h is a positive number, so my graph is going to be like this. The slope equals to h. And there's an intercept over here. The x-intercept is the x value when the y value is 0. So if I make the maximum kinetic energy 0, that means HF equals to phi. When HF equals to phi, this frequency is the cutoff frequency. So this x-intercept is the cutoff frequency. Of course, this x-intercept must be a special frequency. So it must be the cutoff frequency. As for the graph, stopping voltage versus F graph, we can use this part. I can divide by E on both sides, so I get V0 equals to H over E times F minus the work function divided by E. So I will get the same shape graph, but the slope would be H over E. And to find the x-intercept, I can set the y value, the V0, equal to 0. If this is 0, I can make these two equal. H over E times F equals to phi over E. Again, I get the frequency that is phi over. If HF equals to phi, this must be the cutoff frequency. And again, this x-intercept has to be a special frequency, so it can only be the cutoff frequency.